Hello everyone, I wanted to do this video on this problem that I actually gave to a class today. It's a very interesting problem. So here we're given this line integral over this curve parameterized by this crazy looking vector function. And notice the vector field here .dr is only two-dimensional. And also notice that t is going from 0 to 1. And I mean, it could be that this is a closed loop. I don't think it is. I mean, if it is, you can use Green's theorem, of course, but I don't quite think that's the case. But we can actually figure that out by, whoops, didn't mean to do that, sorry. By plugging in t equals 0 and t equals 1. Let me just write r. It keeps happening, sorry about that. Let's just write r of 0. So r of 0 is what? So sine of 0, that's 0. And then well, these next few terms are 0. And cosine of 0 is 1. And 1 minus 1 is 0. So you just get 0, 0. Okay, so it's just a point 0, 0. What about when t is equal to 1? So for t equals 1, let's write r of 1. And we get, well, sine of 7 pi, that's also 0. Sine of any multiple of pi is 0, so that's 0 there. And then when you plug in 1, those three terms turn into 1 each. So it's 1 minus 1 plus 1 plus cosine of 8 pi, of course, that's 1. That's the same as cosine of 2 pi, which is 1. And then minus 1. So great. And notice there's cancellation here, so just left with 1. So let me just write 0, 1 here. There we go. So in reality, this curve is going from 0, 0 to 0, 1. So let me plot that here. 0, 0, and 0, 1. It's really on the y-axis. And the curve may look actually kind of crazy, like something like this, perhaps. And notice there's a direction. It goes from bottom to top, right? But what would be great is if we could actually just parameterize this by something else, and notice it's independent of path. So if we can show that that's conservative, then we can use this idea of independence of path. Now, what other path could we use instead of the one that we're given that goes from 0, 0 to 0, 1, would just be this straight line. Let me draw that here. There we go. So the straight line going from 0, 0 to 0, 1 in that direction is parameterized by what? Well, every point on this line is of the form 0, comma something. So in fact, we could parameterize this by essentially a new vector function. Let me write r of t, but a new r of t now, which is 0, comma t. Or notice t here still goes from 0 to 1. Let me write that here just like this. Good. Great. All right. So now, how do we show it's independent of path? Is we'll actually figure out if this vector field is indeed conservative. So notice there's two components. Let's call it p and q. So if qx is equal to py, then we indeed have a conservative vector field. So is this true? Let's check it out. So notice for q sub x we need, well, product rule. So that's going to be derivative of the first, 2x, times regular of the second, which is e to that power, and plus, because of product rule, regular of the first, x squared, derivative of the second, which is e to the something is itself, times by chain rule, derivative of the power, which is 4x cubed, y to the second. Now, hopefully this is equal to p sub y, so let's check it out. Is this going to work out or not? So p sub y, notice the first term is 0, so I won't even write that because it's independent of y. In the eyes of y, it's a constant, so it goes to 0. And then 2xy e to the x to the fourth y squared, that requires product rule because we have y twice there. So it's derivative of the first, where you just drop the y. Derivative of 2xy is just 2x. There we go. Times regular of the second, e to the x to the fourth y squared. And then plus, by product rule, regular of the first, 2xy e to the, derivative of the second, which is e to that, times by chain rule, with respect to y, is x to the fourth times 2y. Now, are these the same? Well, notice the first two terms right away are the same, so that's fine. But now we have to check these second two terms. And yeah, if we group things correctly, that's 4x to the fifth y squared e to that. And this one is actually also the same. Notice 2 times 2 is 4. And x times x to the fourth is indeed x to the fifth. And you have two y's as well, and that's y squared. So in fact, they do match, believe it or not. So surprisingly, this is conservative. So our vector field, which I'll call f, is indeed conservative. Great. So that means the vector field, or the line integral along C of f dot dr is independent of path. Is independent of path. So we can change C, instead of being from the one described in the problem to the one I described over here, 0, t. So now we'll find dr first. Notice that's the derivative of r. So dr is 0, 1 dt. And now we can write our integral with limits 0 to 1. So I'll write that here, 0, 1, there we go. And then f, remember now when, well, let's see, when, if x is 0, then we get 1 over 0 plus 1, that's just 1. There we go, 1, and then plus, I guess, 0, because 2 times 0, so that completely goes away. And then comma, oh, look at that, that's times 0 as well, so it's all zeros. So it's really just 1, 0. Dot dr, which again we just found is 0, 1, so 1, 0, dot 0, 1. That's just 0 though. So in fact this is this integral is just 0, which I think is a little anticlimactic, but that's just the answer I guess we get here. So we get 0. So we're going to have the integral of 0 plus 0, and that's just 0. So there we go. So I hope you enjoyed this video. Again, it's a little, I don't know, it's a little simple I think at the end there, but definitely really nice to see the technique. Not a very obvious answer, not a very obvious problem. And I thank you all for watching, and I'll see you in the next one.